Okay. So last time I talked to you about the optimal asymptotic approximation, but I didn't show you a picture, and I think it's good for you to see how these things actually work, see an actual picture. So take some random function, say a Bessel function, and that's not the J Bessel function, the conventional Bessel function, but I is the associated Bessel function, okay? And this is I5, okay? So some random Bessel function. And this Bessel function has an asymptotic series that begins e to the x, okay? I5 grows exponentially like e to the x, but times the power of x, which is some square root of x times some constant, times a series in powers of 1 over x, okay? And there's some coefficients here. Okay, so that's how the Bessel function, the 5 Bessel function behaves. And the question is, how well can we approximate the Bessel function using this asymptotic, technique? And so what I plotted here was the question is, how well does this asymptotic series work, and when does it become good? Of course, this is an asymptotic approximation as x goes to infinity. So there's no problem at infinity. The question is, when does it become useful? Okay? And what I've done here is made a plot of the optimal asymptotic approximation compared with the exact answer. So let's see. Let's get a pointer. So just so you see how it works, this is e to the I5 times e to the minus x. Okay, if I just plotted I5, it would just be blowing up exponentially, so it would go right off the graph. You wouldn't be able to see it. It wouldn't be an efficient way of plotting things. So I'm plotting I5 times e to the minus x, and that's this curve right here, okay? And the question is, can we approximate this curve by the asymptotic approximation? Well, you notice as x gets bigger, the optimal asymptotic approximation takes more terms, okay? So when x is equal to, say, this is between 2 and 3, there are 7 terms in the optimal asymptotic approximation. So you understand what that means? The terms in the asymptotic series are getting smaller and smaller and smaller, and they get smaller, and finally, by the 7th term, they turn around, then they start coming back up again. Okay, so this is n equals 7 terms in the asymptotic approximation. As x gets bigger, you need 8 terms, and then 9 terms, and then 10 terms, and so on. Okay? Now, eventually, by the time x reaches 4, you can't see the difference between the asymptotic approximation and the exact answer. But you understand there are jumps here. Do you see this curve, this approximation looks jumpy? That's because we've added one more term. As soon as you add one more term, the asymptotic approximation changes. But by the time x is about 4, you can't see the difference between the asymptotic approximation and the true exact curve. So 4 is very close to infinity. Okay? How close do you have to get to infinity to count is infinity? Well, 4 in this case. It's pretty darn close. But the problem here is that it's very hard for you to judge how accurate this really is without a table. Because, you know, a picture shows what's going on, but what about the actual accuracy? And I want you to see how asymptotics works, okay? So this is how asymptotics works at x equals 3, x equals 4, x equals 5, x equals 6, x equals 7, okay? And this is what happens as you add more and more terms in the asymptotic series, okay? Now, the term that's underlined, that's the optimal asymptotic approximation. So you notice these are the terms in the asymptotic series. Pretty big terms, smaller, 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 smallest. Okay, so that's the smallest term. So then we start taking more terms. We cannot take any more terms. Okay, that's the optimal asymptotic approximation. So here, this 10 to the minus 4, that's the smallest term, and all the way up to here is the optimal asymptotic approximation. Got it? And this is the error that we expect to have. Okay? Here, the terms in these are individual terms in the asymptotic series. They get smaller and smaller and smaller, and then they start turning around and they get larger and larger and larger. Okay? Smaller and smaller. Here's the smallest term. Here are all the terms you take in the asymptotic, in the optimal asymptotic approximation. You stop here, okay, and then the terms are getting larger and larger and larger. So the question is, how well are you doing? What is the error? Okay? And this down here is the relative error in the optimal asymptotic approximation. Now look how fast the asymptotic series is getting better as you approach infinity. At x equals 3, the error is 21%. Well, it's not so great. That's how well the optimal asymptotic approximation does. Okay? When x equals 4, the error is 0.5%. So it has gotten much, much better. Okay? When x equals 5, the error in the optimal asymptotic approximation is 0.0, rounded off, 0.07%. Okay? And when x equals 6, the error is 0.002%. And when x equals 7, the error is 0.00007%. So the error is going down at a fantastic rate. Okay? So by x equals 7, you are so close to infinity that you cannot really see the difference. Okay? Now, hang on for 1 second. Of course, this is just the naive way of extracting information from an asymptotic series. We know better. Okay? We're much smarter than that. This is just for bumpkins, you know, country bumpkins who don't really know what they're doing, so they do the optimal asymptotic approximation. We can pod A the asymptotic series, and in all of these cases, we can extract the exact answer, or arbitrarily close to the exact answer. Okay, now I'm sorry, you had a question. Yeah.
Grows, then we have to consider more terms in the optimal asymptotic series. Then, I mean, we have to do more work to get the correct answer.
That's right. That's right. But you are rewarded for each bit of work you do. Okay, you come in on Friday morning very tired and sleepy, and you've worked all night Thursday night. Okay, and you've calculated the 17th term. And until now, no one in the world had known anything up to the 16th term. But you've just calculated the 17th term. You can now do one more pod A in the diagonal pod A sequence. And you will now know the answer accurate to maybe another decimal place, or half a decimal place, something like that. So each time you do an extra bit of work, you get a reward. Now, if you only knew the optimal asymptotic approximation, you may already be beyond what is optimal. Okay, so your thesis advisor would say to you, what a waste of time. Okay, and you look your thesis advisor in the face and you say, oh no, the optimal asymptotic approximation is just a naive way of of getting information from an asymptotic series. I can pade it and make explicit use of the term that I just calculated. So you always get a reward. You always get the answer more accurately. Okay. Yeah?
Are we supposed to stop when it starts increasing again?
Yes. So again, you see what's happening is that this is a divergent series.
Yeah.
And what you see, what I plotted is just each of those terms. You know, A0, A1, A0, A1 over X, A2 over X squared, A3 over X squared. That's what those numbers are plotted. Each of these numbers. Okay?
But I just
Yeah.
feel that they still continue to decrease after you say that they stop.
Where?
Go 5, for example.
Where? Where? This is. Oh, this may be a bit sloppy. Yeah, that's possible.
But it's still up to the 20. Just
Yeah.
Yeah. Okay. This may be sloppy. So there may be an error in here.
The entries are the partial sums.
Yeah, I get
The entries are the partial sums.
Oh, the entries are the partial sums. Oh, I apologize. Okay. Yeah. Yeah. The entries are the partial sums. You're right. So you can't see them. You can't see the terms. You can't see them getting smaller. Sorry about that. I didn't even read the head of the thing. Okay. So what is plotted, the underlined term is where this number gets smallest, but I didn't plot those numbers. I plotted the partial sums. Sorry. So you can't actually see those numbers getting smallest. You just have to take my word that what is being plotted is a sub n over x. What you do is you make a plot of a sub n over x to the n, and these are dots that get smaller and then get larger, okay? And each of this thing tells you how much error there was in the partial sum up to but not including this term, okay? So when this is smallest, right there, that's when the partial sum, including all of the a's up to but not this one, is smallest. At least that's when we estimate that it's smallest, okay? We don't know an exact calculation of when it's smallest. We only know how to estimate asymptotically when it's smallest. Yeah?
Do we plot the value of that or just
Sure. Okay, because this may be
negative?
alternating in sign, and so what we really want to plot is something like this. Because we're interested in when, in absolute value, when this becomes smallest. Okay. I want to emphasize. You spoke to them in the tutorial. You worked on the Airy function. I just want to make sure that you understand how powerful you are now. Let's see. Yeah, let's make up a problem, because I think just want to make sure that you understand how good you are now at solving problems. Okay, you know what I'm going to say. You're walking down the street, and a guy comes up to you and says, I'm working on an inhomogeneous linear differential equation, which is related to the Airy function, okay? Suppose the guy is working on the equation y prime prime equals xy. That's the Airy equation, okay, plus 1. Okay, so that's an inhomogeneous equation, okay? And he wants to know okay, the question is, how does y of x behave as x goes to infinity? Very interesting problem. So Sarah gave you some lectures on differential equations. You know a little bit about the theory of inhomogeneous linear differential equations. So if you hadn't taken this course and you didn't know anything about asymptotics, you could recite some standard theory about, what to do with a second-order linear inhomogeneous differential equation. You know that in complete generality, if you have an equation like y prime prime plus a of x, y prime plus b of x, y equals c of x, an inhomogeneous second-order linear differential equation, what you would say is this. Or maybe you should, I don't want to say it, you should tell me. What do you say? What do you know about equations like that? What is the nature of the general solution to this differential equation? What is its structure? What can you say about it? Okay, yeah. Excellent. Okay, so what you know, that was real fast. Okay, so what you know is that to solve an equation like this, the first thing you do is you take away the inhomogeneous term. Okay? And you have a second-order homogeneous, not inhomogeneous, but homogeneous differential equation. And there are two linearly independent solutions. So the most general solution to the homogeneous differential equation is a linear combination of those two solutions. So we'll call one of the solutions y1. Okay? We'll call the other solution, amazingly, y2. How about that? Okay? And then you take a linear combination, c1y1 plus c2y2. And this is the most general solution to the homogeneous differential equation. And then you add on a particular solution. So let's call it y particular to the inhomogeneous equation. And that's it. That's the most general solution. Okay? And is there anybody who doesn't know this theory, this basic theory? Let me give you a puzzle. Okay. Suppose you're solving some equation like this. And you're working hard at it, and you're not making much progress. And this is during an exam. Okay, and the clock is running, and the guy next to you is very smart. Okay, and he leans over, and he whispers in your ear, "That's one solution to this differential equation." Okay? And you look at him and you wink at him, and then he says, "By the way, that's another solution to the differential equation." And you wink at him again, and he says, "By the way, that's another solution to the differential equation." What do? Can you make use of this fact? Suppose he had only whispered F. Suppose he only told you that. What is F? Say again?
One of the general.
It is
Some constants, C1 and C2.
Yeah, but if he says this happens to be a solution to this equation, this is a particular solution. This is an example of y particular. And he's giving you. Does this help you solve the differential equation?
Yeah.
Well, it's a particular solution, but it's only one solution. Okay? And it doesn't really tell you anything. Just knowing one particular solution to this equation doesn't tell you much. Okay? When he whispers the second solution, what can you do with it? Say again? You can subtract it. Now if you subtract this from this, you now have a solution, f minus g. You now have a solution to the homogeneous equation. Right? What do you do with that solution to the homogeneous equation? Yeah?
You do a variation of parameter.
Well, that's fancy, but you do reduction of order. Okay, just simple reduction of order. You can also do, if you want to be fancy, but you can do reduction of order and find the other solution to the homogeneous equation. So this is one solution, that would be y1. Reduction of order would give you y2, and now you can add on f, and that will be the full solution. Okay? But suppose the guy, where's the grades? Suppose suppose the guy has whispered all three different particular solutions to the equation. Can you solve the problem? Yes! You're done. Why? Why are you done? What do you do with these three different particular solutions to the equation? Yeah.
Well, we can subtract g of f, g from f and g from h, and we would get to part of the
Beautiful.
homogeneous, and then we can make them perpendicular.
Bravo, bravo. Beautiful work. That's right. You're done. You're completely done. Because f minus g is a solution to the homogeneous equation. And furthermore, g minus h is another solution to the homogeneous equation. So the general solution would be c1 times f minus g. That's one solution to the homogeneous equation. c2 times f minus h, there's another solution to the homogeneous equation. Okay? And then you can add on anything you like. Say f. That's a particular solution, and this is the most general solution to the problem. Got it? So once you know three particular solutions, it's exceedingly useful because you're done. Okay? Do you see how it works? That's the connection between homogeneous and inhomogeneous equations. Okay? Now, what do you know about, so this is general. But you have been, remember, you're walking down the street and some guy gives you this equation here. Okay? So you want to write down the most general solution to this equation here. Okay? And you know this theory, what can you write down? Well, you know that for the homogeneous equation, one solution is called AI of x. Right? And its asymptotic behavior is e to the minus 2/3 x to the 3/2 times x to the minus 1/4 times some constant. And another solution, bi of x, is some constant times e to the plus 2/3 x to the 3/2 times x to the minus 1/4. Great! Because now we've got this much and this much, and all we need is a particular solution of the homogeneous of the inhomogeneous equation. We need some particular solution, and we need the asymptotic behavior. How do we find it? Okay, how do we find it?
Oh, we guess it.
Good. I like that. How do we? But is there some general procedure?
Say that the solution has y double prime equals 0.
Well, not y double prime equals. Well, what do you mean y double prime equals 0?
But that's what
If y double prime equals 0, then we know that y is equal to ax plus b, and that's not a solution to the equation. That doesn't work. How do we, remember, we know asymptotics now. We're powerful. How do you solve an equation like this? What do?
You can put in a polynomial and then just see what it has to, what the coefficients are.
Won't work. Polynomial? Can't work. Can't possibly work, right? Because if you put in a polynomial, suppose the degree of the polynomial is n, okay? Then the degree of this polynomial will be n plus 1, right? The degree of that polynomial will be n minus 2, and the degree of that polynomial will be 0. So you could never balance the polynomial with degree n plus 1. You could never do that. So a polynomial can't work. If it could, then this would be a bad example, because you get away with it. But there is an approach. What do we do in asymptotics? There's only one thing we can do. The method of dominant balance. There are 3 terms here. Which term do you think is the important term, and which term is the unimportant term? Okay? So let's think about it. One possibility is we can throw away that term. But we already have the result of throwing away the inhomogeneous term. That's written right here on the board. Okay, so we're done with that. What else could we throw away? We could throw away that term. Now you're shaking your head no. Why do we not want to throw away that term?
Because x is going to infinity.
Because x is going to infinity, but how do we know that that's wrong? The answer is, we tried throwing away that term. Let's do it right next to it. Y prime prime equals xy plus 1. Okay? And we tried throwing away the xy term. Let's try throwing it away. If we try throwing it away, we would conclude that y double prime is asymptotic to 1. So y prime would be asymptotic to x, all as x goes to infinity, right? And y would be asymptotic to x squared. And do you see what we've done? This term would therefore be an x would be asymptotic to x squared over 2. This term would be like x cubed over 2. So we're throwing away x cubed over 2 as x goes to infinity, but we're keeping 1. Nah, that doesn't work. That's terrible. Okay. Well, there's one other possible way of going about it. Let's throw away this term. That's really interesting. If you throw away that term, if you say, let's try throwing away that term, it isn't even a differential equation anymore. If this is the term that's small, then the asymptotic approximation you're making is that xy is asymptotic to minus 1 as x goes to infinity. Right? Great. Therefore, y is asymptotic to minus 1 over x. Boy, was that easy. Is that consistent? Is it consistent? Okay, we always have to go back and check consistency. If y is asymptotic to minus 1 over x as x goes to infinity, y double prime is asymptotic to 1 over x cubed. Therefore, was it correct to throw away 1 over x cubed compared with 1? Yes. Boy, was that fast. Okay, now maybe you doubt that this is working. Okay? This was really fast. We got away with solving a differential equation just like that. All right, what do we do next? What do we always do next? Okay, we reduced an equality to an asymptotic approximation, and we solved it. Next, what do we do?
Y is that class of correction.
Good. Now say it loud again.
Y is that class of correction.
Very good. Okay. Good. You're getting the idea. That's good. Okay, so now you say, let y equal, we go back to the equal sign, We say y is equal to minus 1 over x plus a correction term. Okay? What should we call the correction term? Say c of x for correction. And c, we expect c of x is negligible compared with 1 over x as x goes to infinity. It's negligible. Not less than 1 over x, but negligible compared with 1 over x. Smaller than 1 over x. So it's quite small. Okay? We now plug this into the equation. Okay? So y double prime would be, well, so y prime would be equal to 1 over x squared plus c prime, and y double prime would be minus 2 over x cubed plus c double prime. We plug it into the equation, and we get c double prime minus 2 over x cubed is equal to xy. Xy would be minus 1 plus xc plus 1. Okay? Now, notice this is a pretty complicated equation, but two terms exactly cancel. Why does this term cancel that term? Because we got the first term in the series right. Okay, that's the check. We always get one exact cancellation. Now we have a new equation. Okay? Now, what do you think might be the way to say it again? Yeah, maybe we can just throw away c double prime. Is that consistent? Okay, this is an equality, and what you say is, can we throw away this and replace that by an asymptotic approximation? If we can, we would conclude that c times x is asymptotic to minus 2 over x cubed, and therefore c is asymptotic to minus 2 over x to the 4. Is that consistent? If c is asymptotic to that, c double prime would be asymptotic to 1 over x to the 6th, some constant over x to the 6th. Was it valid to throw it away? Yes. Great. We now have the next term in the series. Okay? Is it true that c is negligible compared with 1 over x? Is that correct? Yes, it is. Okay? So now the next term in the asymptotic series is minus 2 over x to the 4. Isn't this cool? Do you see what we're doing? We now know that y is asymptotic to minus 1 over x minus 2 over x to the 4. Can you guess what the next term in the series is going to be?
Something over BC.
Something over,
X to the power of 7.
say a little louder, x to the power 7. You're right. Okay. Next term is something over x to the 7, and the next term is something over x to the 10. Do you see that? We got the whole asymptotic series. Okay, yeah.
But why didn't we throw away the other term, including
Try it. It won't work. It'll lead to a contradiction.
It would give us the area function.
Yeah, of course, we are not interested in the area function. We already know that. Okay, we're looking for a particular solution. Okay? So this is an asymptotic series. Do you think this is a series? Does it converge or diverge? Well, you could try. You can go home and work it out. This term will be much bigger than this. This will be much bigger than that. These terms will be growing roughly like some sort of factorial. So this is a divergent series, and this is the asymptotic behavior of a particular solution. Okay, have you followed that? Do you see how easy it is? Asymptotics is fantastic. We never solved a differential equation here. We were just differentiating things. You see that? We solved a really hard inhomogeneous differential equation just by playing. There's no work at all. Okay? But now we have to add that and this together. Now, the question is, what is the answer? Remember the guy on the street? He said that he needed to solve this differential equation. He said, how does y behave as x goes to infinity? What's the answer? How does y behave as x goes to infinity? Yeah?
Depends on initial conditions.
Sure, it depends on initial conditions. So we have not done global analysis yet. We don't know how to take data at 0 and connect it with data at infinity. We're only working out behavior at infinity. We're only working out behaviors at infinity, so we expect there to be unknown constants, arbitrary multiplicative constants, at most 2 of them. Okay, but how does y behave at infinity? Yeah?
Like BI.
Like BI. Exactly. All this is very interesting, but you notice that this says that a particular solution, our particular solution, behaves like 1 over x. Since it behaves like 1 over x at infinity, it's unimportant compared with BI. And AI is also unimportant compared with BI. So the answer to the guy is, the general answer to the guy is that, and this is a very, very important word, this is said to be subdominant compared with this, because this is exponentially small compared with this. And this is also subdominant. This is even, AI is even more subdominant. So this is exponentially small compared with BI, and AI is exponentially small compared with this. Do you see that? So since it's subdominant, it doesn't matter. The contribution of AI, is smaller than any term in the asymptotic series for BI. Small. They're just negligible. Okay? So it behaves like this. This is the answer. How does y behave? It behaves like this. And the particular solution doesn't contribute because it is exponentially small compared with AI, compared with BI. Okay? Do you understand? Sorry, I circled it. Behaves like this, and this is not here, and this is not here. Okay? So the answer to the guy's question is, how does it behave? It behaves like some constant times x to the minus 1/4 times e to the 2/3 x to the 3/2. So this is growing very, very fast. The guy says to you, did you understand that? But now the guy says to you, oh, I forgot to tell you something. This comes from a physics problem, and nothing in a physics problem is allowed to blow up at infinity. Can't do that. Can't blow up at infinity. Okay? So I forgot to tell you that y of infinity is 0. Y plus infinity is 0. Okay, the solution goes to 0 at infinity. Now, what do you say to the guy? If he says y of infinity is 0, he gives you one piece of information, then you know that, in general, the growing solution can't be there. One of these homogeneous solutions can't be there, so there is no BI present. There could only be an arbitrary amount of AI plus this particular solution. What do you say to the guy?
You could have told me this before.
You said you were concealing important information. How dare you conceal crucial information? Okay, so the question is now, what do you say to the guy? What's the answer? If he tells you that y of infinity happens to be 0, he says y of infinity is 0. Now what do you say to the guy? How does y of x behave?
Negative 1 over x.
Say it again?
Negative 1 over x.
Right. That's it. That's the answer to the question. It behaves like minus 1 over x as x goes to infinity. The guy says to you, wait a minute, you can't be right. Because you're telling me that the answer contains no arbitrary constant. Okay? The guy says to you, no, you must be wrong. He doesn't know anything about asymptotics, but he says to you, you've got to be wrong because I gave you one boundary condition. That means that the solution to this second order differential equation must still contain one arbitrary constant. What do you say?
Subdominant?
Hmm?
Subdominant?
It's subdominant. That's right. You say, of course, that's true. There is an arbitrary constant, but that arbitrary constant multiplies a function which is exponentially small and subdominant. So you say, yes, indeed, there is an arbitrary constant. There is something, some arbitrary constant here times e to the minus 2/3 x to the 3 x times x to the minus 1/4 times its series, its asymptotic series. But this is exponentially small compared with that. So you say to the guy, independent of whatever your initial conditions are, if you know that your solution is going to 0 and infinity, then I can tell you the asymptotic behavior with absolute precision, with no arbitrary constant present. I know that y of x behaves like minus 1 over x, and then minus 2 over x to the 4, and so on. And there is no arbitrary constant in this asymptotic behavior as x goes to infinity. Isn't this fantastic? I could write down some transcendental functions, right? If I knew what Sarah was teaching, okay, at the beginning of the course, I know that the solution is a linear combination of an Airy function and a Berry function. And then to generate the particular solution, I can use the method of variation of parameters, right? Generate a particular solution, and whoa, boy, what a mess. This would be really awful. Or I could just say it behaves like minus 1 over x. Done. And the answer is unique. Yeah,
I don't know if it's a stupid question, but
I'm certain it isn't.
I'm not sure I understand that. Like, we have a series that we don't know how it behaves. Are we sure that it doesn't converge to something else
It
at
might.
infinity?
It might converge.
Like,
Oh, you mean, how does this be at infinity?
yeah,
Oh, no. If this is a convergent series, we know,
but it's divergent. That's what we said.
right, it is a divergent series. Okay, it is a divergent series, but we know how it behaves asymptotically at infinity. Okay, the definition of an asymptotic series, okay, the definition of an asymptotic series is that the difference between y and the first term of the series is asymptotic to the next term. Okay, so the difference between y and the first term would give you y, plus, let's write it as y minus 1 over x. The difference between y and that thing is asymptotic to minus 2 over x to the 4th as x goes to infinity. And therefore, I claim y behaves like minus 1 over x. And furthermore, the difference between y and 1 over x is going to 0 even faster. So I know this is vanishing like minus 1 over x. No problem with that. Okay? So this is, do you see how powerful asymptotics makes you? You don't have to know anything. You just just dig into the problem, and out pops the answer. Just like that. I've never written down any transcendental function here. And this is a transcendental differential equation. So if you wanted to solve it exactly and go to the books and so on, you could do it, And you could say, you know, the solution, the exact solution is y of x is some constant times ai of x plus some other constant times bi of x plus and a very complicated variation of parameters integral, right? There's an integral with respect to, you know, there's an ai and an integral of some function 1 bi over the Wronskian minus bi times ai times 1 over the Wronskian. If you remember your variation of parameters calculation. This is horrendous. This is really awful. And you've written the answer in terms of transcendental functions. Which do you like better, that or that? You see what asymptotics does? It makes everything perfectly transparent. You know how it's behaving. I've given the answer. Okay. Furthermore, I've said something about subdominance, and this is very, very, very important. So, before we go into any more theory, I want to talk about subdominance, because this is really, really good. Terrifically important point. This is a key word. In the study of asymptotics. Subdominance means exponentially small compared with. Okay? So, if I say to you, how does the solution to this equation, to the area equation, behave, you notice that the first term, let's see, where did we, yeah. So the function bi behaves like e to the 2/3 x to the 3/2 times x to the minus 1/4 times a series, an asymptotic series, in powers of 1 over x. It's actually 1 over x to the 3/2, but and there are some coefficients. Okay? Notice that every single term in this series is huge, exponentially large, compared with this. Okay? Therefore, if you say that you're solving this differential equation, y prime prime equals xy, if you only know how to solve things exactly, you would say the exact solution to this equation, y, is some constant times ai plus some other constant times bi of x. That's the general solution to this equation. If you write down the asymptotic series as x goes to infinity, you would say that every single term in that entire asymptotic series for b is bigger, exponentially large, compared with that function. Therefore, this is the subdominant function, and this is the dominant function. Okay? So when you write down the behavior, the asymptotic behavior of a solution to that equation, you would never include that function, ai of x. You could never include that. And therefore, the asymptotic approximation to the solution to this equation for large x doesn't contain two arbitrary multiplicative constants. It apparently only contains one. Only one. Because this is always negligible. Did you follow that? This is negligible. So the general solution to this equation, even though it's second order, only contains one arbitrary constant, d. Okay? Unless someone walks up to you and says, by the way, y of plus infinity happens to be 0. Okay? That means, this implies that d must be 0. In which case, the asymptotic behavior contains, again, one arbitrary constant, namely the constant multiplying ai. Because now, if you know that d equals 0, the solution must contain ai, can only be a multiple of ai, and again, it contains one arbitrary constant. Okay? Now, the logic I just gave you is called this. Have you ever studied set theory? Do you know that there's a distinction between naive set theory and the Russell paradox and something called more sophisticated set theory? You know, okay, sometime I'll tell you about that. It's very interesting. This you might call this naive asymptotics. Okay, this is called Poincare. Asymptotics, and this is, I would say, what I've just said to you is early 20th century asymptotics. Okay? In fact, I would like to make this a really interesting course and tell you something about modern asymptotics. In modern asymptotics, we can actually include the effect of terms that are exponentially small. In other words, even though this is smaller than every term in the asymptotic series for BI, we may be able to include the effect of that. And this is called hyperasymptotics, where we include the effect of the subdominant term. And maybe on the last day of the course, I'll tell you a little bit about hyperasymptotics, which is very interesting. Hyperasymptotics has only been developed in the last 2 or 3 decades, okay? And very little is known about it. And when you do asymptotics, okay, this means asymptotics beyond all orders, which is really interesting. It's really, really interesting and wide open field to study. It's an absolutely fascinating field, and I'll show you maybe a little bit about it. This is really, really, really interesting. Okay, are there any questions? Okay. Before we go on, however, so we're not going to say any more about hyperasymptotics, and we're going to go back now to what we've been doing in this course, which is really Poincare asymptotics. Because Poincare, if you said this to Poincare, he would have said, "What? Are you out of your mind? If it's exponentially small, you forget it. How could you take a term that's beyond the last term in an infinitely long series?" Okay, do you understand? You're going beyond infinity. How could you go beyond infinity? Okay, you can. It's really interesting. Okay, but he wouldn't have believed it. But let's talk a little bit more about Poincare asymptotics and subdominance. In physics, physics is all about subdominance. That's what physics is about. Why is this? Can you understand why physics is about subdominance? Yeah. No, it's not because our laws are not exact. Yeah, why would you think that?
Because things typically don't blow up at infinity.
Exactly. Exactly. In physics, if you're solving, the thing that, what is the world described by? It's described by the Schrödinger equation. At least so far it is. Maybe there'll be a new theory. But the world is described by a Schrödinger equation of the form y prime prime is equal to some function of x times y. And we are always interested in solving the Schrödinger equation. How does the Schrödinger equation behave at infinity? Now, typically, Q involves some potential v of x. And v of x is some sort of rising potential. V of x might go like x squared if we're talking about the harmonic oscillator. Okay? So how does the solution to the Schrödinger equation behave WKB says that y of x behaves like some constant, plus or minus, q to the minus 1/4, e to the plus or minus integral of the square root of q of s ds up to x. That is what WKB says. And we derived that in class. One solution has a plus sign. It's blowing up at infinity. One solution has a minus sign. Which solution do we take? We always take the subdominant solution. In fact, if someone says to you, what's quantum mechanics? You can tell them it's subdominance. That is what quantum mechanics is really all about. It's not, there is no plus sign. Things do not blow up at infinity. Things have to go to 0 at infinity. That's because everything is localized, right? Everything we do is localized. Nothing ever blows up at infinity. When you write down Maxwell's equations, you've heard of them, right? Those are homogeneous differential equations. And they're always, the Maxwell equations are always of the form derivative of is equal to the derivative of, and the derivative of is equal to the derivative, and there are 4 such equations, right? One solution to this equation is the electric field is equal to 1, and the magnetic field is equal to 2, right? That's because the derivative of whatever it is 0, and the derivative is, so I solved them. E equals 1, and B equals 2. There you go. Right? That's a solution to Maxwell's equations. I solved them. Except this isn't vanishing at infinity. It violates whatever the boundary conditions are at infinity. The electric field cannot be 1 at infinity. Why? Because the voltage, what's the voltage? It's the integral of the electric field, right? So the voltage would be growing linearly at infinity. Are you kidding? The voltage can't be infinite at infinity, right? The voltage, the potential, is the integral of the electric field. So the voltage would grow like a constant times x at infinity. Can't be, right? So things must vanish at infinity. That's nonsense. Can't do that. So in fact, what is quantum mechanics? It is subdominance. Everything must vanish at infinity, and in fact, we know how it vanishes at infinity. It always vanishes exponentially fast. That's how localized we are in the world. That's what the Schrodinger equation tells us. Okay? So remember that. Remember that we are always interested in subdominant solutions. We are never interested in dominant solutions for large x. Never. Okay? Okay. Now, what I want to do is indicate to you, I want to say a little bit about, let's see, can I erase this? Okay, I want to say a little bit about the connection between asymptotics and physics, okay? And the connection comes, I'm just going to summarize very briefly what the rigorous theory is. Okay, and the rigorous theory, I have to tell you, is it's really quite limited. Okay? So the rigorous theory of asymptotics is limited to a class of functions called Stieltjes. Stieltjes functions. Okay, so Stieltjes is really the guy who contributed most to the rigorous theory of asymptotics. Amazingly, however, eigenfunctions, that is, solutions of the Schrodinger equation, happen to fall into this class. It's fantastic. Okay? That's the really wonderful thing. So what's a Stieltjes function? Well, this is a Stieltjes function. F of x is a Stieltjes function if it has the form integral from 0 to infinity dt rho of t divided by 1 plus xt. Okay? That's a Stieltjes function. Okay? Where rho is called a weight function. Okay? And rho has the property that it is strictly positive, positive or zero, not strictly positive, but strictly non-negative. Okay, rho can be zero, but it can never be negative. Okay, for 0 less than or equal to t less than infinity. For all t from 0 to infinity, rho of t must be greater than or equal to 0. And it must also be that the moments of rho exist. Nth moment of rho exists. So the nth moment of rho is going to be called an, and the nth moment of rho is the integral from 0 to infinity dt rho of t times t to the n. That's the definition of the nth moment. So this must not be a divergent integral. Okay? That's a Stieltjes function. Okay? Now, there's something called the Stieltjes series. What's a Stieltjes series? Well, to find out what a Stieltjes series is, let's do something cute. Let's say this is equal to dt rho of t, and let's expand this into a series for small x. What, you say? You can't do that. This series only converges, remember, this series only converges if x times t is small compared with 1, and t could be very, very large. So I say to you, don't worry about it. Okay? Now let's integrate term by term. And if we integrate term by term, then this becomes a series of the form sum from n equals 0 to infinity minus 1 to the n times a sub n times x to the n. Okay? Any series of this form is called the Stieltjes series. This, of course, is a divergent series, because to get here, we did something which in your freshman calculus class would be considered illegal, because we interchange orders of summation and integration, which is, you just term that illegally. You'd say an illegal operation, so you say, no, you're not allowed to do that. Okay? But we did it. Okay? Why did we do it? Because although this is typically a divergent series, not always, but almost always, this is divergent, this series is asymptotic to this function. Okay? f of x is asymptotic to the series, sum from 0 to infinity, minus 1 to the n, a sub n, x to the n, as x goes to 0. So this is a Stieltjes series, and this is a Stieltjes function. Okay, now let me tell you what is known as far as rigorous. Let's see, if I write here, not everybody can see. That's not a good idea. Let's write over here. Let me tell you what is known about Stieltjes functions. Okay? If you, by the way, we should do an example. What's an example of or let's put it over here. What's an example? Okay, one example of a Stieltjes function would be to take rho to be, say, rho of t to be e to the minus t. In this case, what is a sub n? You see, this is a positive function, and its nth moment exists. What's a sub n, the nth moment? Say it again. N factorial. N factorial. Okay, so that's one example. What's another? And in this case, the corresponding Stieltjes function would be the integral from 0 to infinity dt e to the minus t over 1 plus xt. Okay, that's the Stieltjes function, f. What's another example? Another example would be, say, rho of t is equal to 1 for t between 0 and 1, and 0 for t greater than or equal to 1. That's a perfectly acceptable rho. In this case, what is the nth moment? A sub n. What's the nth moment? Let's put this a little higher. What's a sub n, the nth moment? One over n plus 1. A sub n is 1 over n plus 1. And the corresponding Stieltjes series, the Stieltjes series would be the sum from 0 to infinity, x to the n minus 1 to the n over n plus 1. Okay? And what is the Stieltjes function in this case? You know? Stieltjes function in this case? It would be log of 1 plus x over x. Okay? So this is an example of a Stieltjes. This is a very simple example of a Stieltjes function and the corresponding Stieltjes series. And this function is asymptotic to that series. And this series actually happens to be convergent. In this case, you have seen this function before, and the Stieltjes series in this case happens to be minus 1 to the n, n factorial x to the n. That's a divergent series, and it's asymptotic to the function. These are two examples of Stieltjes functions, okay? Now, here's the theory. And it can be summarized. Unfortunately, not much is known, so I can summarize the whole theory in about 3 minutes. Okay. Okay, a Stieltjes function has 4 properties, very important properties. A very important property is that f of x is analytic in the cut x-plane. With a cut on the negative axis. It's guaranteed to be analytic everywhere except on the negative axis. First question to you is, what's wrong with the negative axis? Can you tell me what's the problem with the negative axis? No, what's wrong with the negative axis is if you look at this function, never mind the series, what's wrong with the negative axis is if x is negative, when you do the integral from 0 to infinity, there is some value of t that passes through minus 1 over x. So the denominator is 0, so the integral doesn't exist. That's all. But there's never any other problem. So everywhere else in the complex x-plane, this function is perfectly okay. So that's property 1. Yeah.
Could you not avoid it by making some integration and avoiding?
No, this is the explicit definition on the real axis. You could try to avoid it, but then there still is a singularity there. Okay? So this is the explicit definition is that this is an integral. This is a real function. Everything here is real, except that x could be complex. Okay? And this is a real integral up the real axis. It's a well-defined. If we start pushing around contours past singularities, then we're going to pick up poles. And we're not going to worry about things like that. Okay? So this is a very clean definition. Okay? Yeah.
So if solutions to the Schrodinger equations are Stieltjes function, then how do we interpret this?
Oh, hang on. We haven't said anything about that yet. Okay. So, but I've claimed that this is an analytic function in the sense of complex variables. What does analytic mean? Anybody quickly tell me what is, if I say I have an analytic function, what does that mean? Yeah.
Well, you can differentiate it any
Period. You're right. Analytic means it has a derivative. That's all. A complex derivative. How do you prove that? That's very fancy. How do you prove that this function has a derivative? The answer is, the simplest way to do it is to differentiate it and show it exists. We can do a constructive proof. Watch. F prime of x is the integral from 0 to infinity dt rho of t over 1 plus xt squared with a minus sign, factor of t. I just differentiated it. Period. Why does it have a derivative? Because I took the derivative and that integral still exists. Okay? Yeah.
How do you know that you can switch the order of integration?
Because the integral is absolutely and uniformly convergent. Rho is a positive function. Okay, so it is absolutely convergent. Okay, and it's uniformly convergent. So there is no question with interchanging the order of integration and the order of differentiation. That's why. It's uniformly convergent and absolutely convergent. That's why. Okay, so it satisfies the condition for interchanging differentiation and integration. So it's analytic. Secondly, f of x goes to 0 as x goes to infinity in the cut plane. So as you go to infinity in any direction in the cut plane, f of x goes to 0. Why is this true? Because there's an x in the denominator. So it goes to 0. Okay. Third fact, f of x is asymptotic to the series a sub n x to the n, okay, as x goes to 0 in the cut plane. That means, here's the cut. No matter how you approach 0, this series is asymptotic to the function f. That takes a tiny bit more work to show, but that's easy. Okay? Here's the fourth property. You're going to
What
write
about the
this.
-1 to the end?
Oh, minus 1 here. And the fourth property, thank you. Fourth property, you're going to love. Minus f of x is Herglotz. Can anybody tell me what a Herglotz function is?
I can't see it.
Yeah, let me raise this up. And that's it. This is the last property. And I love this name. Don't you like that name? How would you like to be called Herglotz? It's actually the name of a guy. Herglotz is a very simple property. If you have a function, f of x, that's complex, it is Herglotz if, let's call it g of x, some random function. G of x is Herglotz means that if you take the imaginary part of g of x, it has the same sign as the imaginary part of x. Okay, so that means in the complex x-plane, if you're in the upper half of the x-plane, the imaginary part of g is positive. And in the lower half-plane, the imaginary part of g is negative. And on the real axis, the imaginary part of g is 0. Okay? So here, the imaginary part of g is positive. Here, the imaginary part of g is negative. And on the real axis, the imaginary part of g is 0. That's all. The sign of the imaginary part is the same of the function, is the same as the imaginary part of its argument. These are the 4 properties of a Stieltjes function. That's it. Okay. But we don't calculate Stieltjes functions. What do we calculate? We, as physicists, calculate series. And if you can show that a given function has these 4 properties, that means it is a function of Stieltjes. Okay? So let me say it again. A Stieltjes function always has these 4 properties. That's easy to prove. But if you have a function which has these 4 properties, you know it is a function of Stieltjes. So it goes both ways. A Stieltjes function has these 4 properties. But if you can show that an arbitrary function has these 4 properties, it is a function of Stieltjes. Okay? The amazing thing is that in physics, when we calculate things, solutions of the Schrödinger equation, the solutions of the Schrödinger equation have these 4 properties. And therefore, they are functions of Stieltjes. PADE converges rigorously for functions of Stieltjes. That's the only class of functions where it's known generally, rigorously, that PADE converges. There are other special cases where you can prove it converges, but this is the only interesting class of functions. Okay? Now I'll let you mull that over the weekend, and next time, Monday, I'm going to show you how you establish that in physics we have these 4 famous properties. Okay, And it's the fourth one that's really fun. Okay, this fourth one is really, really interesting. Herglotz. I love that name. Okay. Okay, are there any questions about that? Okay. Any questions? So think about this over the weekend. I think I should, before we quit, let me just emphasize this one more time. If you have a function of Stieltjes, we can prove each of these four properties. Okay? But in real life, what are you doing as physicists? What you do is perturbation theory, because that's the only way you know how to solve a problem. Okay? And you come up with a perturbation series. And you want to know whether or not you can sum that series and apply Pade to that series. So if you can show that the answer to the problem that you're looking for, you don't know how to calculate the answer exactly, but if you can prove that the function that you're looking for, say the ground state energy in electrodynamics or something like that, you're trying to show, if you're trying to calculate that function, you calculate it perturbatively. But if you can prove that the function you are calculating has these four properties, it's Herglotz, okay, it has a series, the perturbation series is asymptotic to it, it's analytic in the cut plane, it vanishes at infinity. If you can prove those four properties, whoops, you can prove, I wonder if they'll take that off the, they won't let me have tea anymore. If they can prove those four properties, then if you can show that you have those four properties, then you know you have a function of that what you're calculating is not just any old function like an eigenvalue, it's actually a Stieltjes function of the perturbation parameter epsilon. It's a Stieltjes function. And once you have a Stieltjes function, it is known rigorously that the Pades converge. Okay? There's one last fly in the ointment. What I said to you was the Pades converge. The Pade sequence converges. I didn't say the Pade sequence converges to the right answer. I just said that it converges.